At the outset, I thank the organizers for giving me this opportunity to share some experience on today's topic, case studies on assessment of as installed offshore pile capacity. As we all know, there are different processes for pile driving. The first is the geotechnical investigations to be carried out. And offshore geotechnical investigation is very well organized, high quality, and is thoroughly planned. The next step is to perform a pre-installation drivability study using wave equation program for hammer selection to ensure that the chosen hammer can safely install the pile to the intended target penetration. And the last step is during the construction, piles are monitored during driving to ensure hammer performance again, the stresses transferred to the pile, and also to evaluate the pile capacity. In the pre-installation drivability study, there's an input goes into the program, the hammer properties, the hammer and pile cushion properties, the pile properties, and the soil properties. And the output will be your resistance versus blow count along the pile length, stresses versus pile length, and transferred hammer energy. And this is a typical blow count versus depth for various driving conditions. You could also get the dynamic stresses from the analysis, not only the driving stress, but also you can add the static stresses in order to ensure that the combined stresses are within the allowable limits. The post analysis, then you go to the site to drive the piles and the hammers are chosen. There are two philosophies the principals follow. One, if they have the data, geotechnical data, and the piles are driven to the target penetrations, they accept the pile. The other principals wanted every blow to be monitored and then evaluate the capacity based on pile monitoring. Both of them are in vogue currently in several geographies. But for engineers, even though we have thorough geotechnical investigations, Mother Earth always do not come together. There are some challenges during pile driving, and I will illustrate two case studies where piles have prematurely refused before the target penetration. So therefore, the assessment of as installed capacity is required for piles acceptance when piles are prematurely refused shallower than the design penetration. And the piles refused prematurely generally satisfy the requirement of compressive capacity, but the tensile capacity is not satisfied. And the minimum penetration required for lateral stability also will be a challenge, particularly if the refusal happens at a shallow depth. In such cases, the refused pile is advanced to deeper penetrations by drill and drive technique up to the design penetrations. Although there are many other remedial measures that can be adopted, like your insert pile, tilt and grouted pile, and so on and so forth. And these two case studies here illustrates the drill and drive technique. So the following case studies highlight the importance of assessing the as installed capacity during the drill and drive process for control over the drill out length, not to lose the skin friction, and the use of pile driving records for back analysis of pile capacity. And this is the second case study. So I'll illustrate two simple case studies. Number one is in the Persian Gulf. The project consists of a four-legged offshore jacket platforms, which has a diameter of piles from 1.524 meter, and the wall thickness varied between 31.75 to 88.9 meter. They commissioned IHC 500 kilojoules hammer to drive the piles through the jacket legs to a penetration of about 88 to 95 meters. As you know, the soil stratigraphy is pretty uniform, consistently increasing shear strength with depth. Soft clays up to 12 meters, stiff to very stiff up to 76, and hard clays below 76.5 meters. But there was an intermittent silt layer at around 45 meter, and the bore log indicated a 0.3 meter thick gypsum at 44, which apparently was not quantified properly. We do not know the reasons, whether it was a poor geotechnical investigation or perhaps it was a lateral variability at the site itself. But then this was only captured to have a thickness of 0.3 meter. And as usual, the pre-installation study revealed that there was no premature refusal. So the project progressed well, and the people went to the site to drive the piles. The first pile was driven on leg A2, and this encountered a refusal at 44.5 meters. And no decision could be taken on the pile's acceptance at refusal depth, as the pile was not instrumented and monitored, and so with all the remaining piles, and people puzzled. And pile toe buckling was suspected due to hard driving because the blow counts are extremely high, and thus the driving was stopped. And there was no plan for remedial measures because it was not at all indicated in the geotechnical investigation. So the entire team was demobilized. I'm sure a lot of people lost a lot of money on this project. But then after several introspection, then the client wanted to come back and progress with the project. So after 1 year, when they come back to the project site, this time they had thorough planning. They wanted to instrument the pile, and also they prepared to bring the drilling rigs to drill out the plug so that they could get away with those cemented layer and then see if they can drive the piles to the target penetration. So again, this pile A2 was instrumented and a restrike test was performed and found that the pile 2 was intact, and this was a good sign for all the team. And the compression and tensile capacity obviously was not sufficient for acceptance because the depth of pile is only less than what was required. So the capacity that was estimated was 26 meganewton and 5.6. It's way less than the required capacity at 95-meter depth. Okay, so when we look at the geotechnical data, it's undrained shear strength increasing with depth, and there's one small silt layer which was not quantified during the geotechnical investigation, and it was assumed to be a silt, and the cemented layer was missed out, and therefore the parameters was very less, which did not indicate the refusal or any challenges that can pose to pile driving. So when you actually look at the geotechnical data, the two CPTs at that left refused with more than 50 MPa, which indicated slightly that there could be some thicker cemented layers, and also the lateral variability from the borehole to the leg locations can also have a thicker cemented layer. And thus it was decided to employ the pile top drilling and use the drilling and drive technique to advance the pile to the design penetration. So already all the plans were made to prepare and put the drilling rig on top of the pile. A pilot hole of 1.2 meter diameter was drilled up to 1 meter below the pile toe. And this is really important. You cannot simply take out the core below the pile tip unless you are extremely confident that is purely cohesive where there is no collapse of the borehole. If it were to be otherwise, I think you need to keep those level above the pile tip. The core cutting stuck in the drill bit confirmed that the material encountered was in fact gypsum. So this is the drill rig that was adopted to core the pile, core the soil inside the pile. And those cuttings that was found in the drill bit was indeed confirmed to be a cemented gypsum. Okay. The data from the measurements also indicated that the shaft frictions extended over a longer length before the drill out, and then after the drill out to a shorter length. Although after the drill out, the pile resumed with a very high blow counts because the gypsum was still there below the pile wall. So the pilot hole was smaller in diameter than the diameter of the pile. The capacity after drill out was less than before drill out, which is due to the reduction in the capacity due to reduction in the skin frictions. I'll show it in the next graph. So although the end bearing was still high, since the pile toe was intact, the computed capacity was within the mobilized capacity during refusal, and the pile driving continued without resorting to another round of plug drill out below the pile toe, which otherwise would have caused more reduction in the capacity. And when you start moving, the pile reached about 1 meter from the refusal depth, the blow counts actually reduced, and the piles could be driven successfully to the target penetration. So thereby it was concluded that the gypsum layer was thick, around 1.3 to 2.6 meter, vis-a-vis around 0.3 meter reported in the bore log. And the strength of this gypsum also was underestimated during the geotechnical investigation compared to what was actually measured during the restrike test. So the predicted and the computed is in the next slide. As you could see, the capacity during restrike before the drill out, and this is after the drill out, there is a reduction in the capacity. This is essentially due to the reduction in the shaft friction. The dotted lines is before the drill out and the thick line is after the drill out. When piles start moving, then it's already followed because the cohesive material exists toward the target penetration. And then there's another add-on. You could see the increase in the blow counts at the add-on due to the setup, and then the blow counts was almost around 50 blows per 0.25 meters, and they could reach the target penetration. These are some small decisions that you need to take. It's about 2 trials. They did the drill and drive techniques, but you need to have some conviction and courage to make the decision on site so that you don't spend extra time on the barge, because the barge time is too expensive on the in the offshore condition. The second case study, again, it was in west coast of India. The jacket had a 4-leg, 2.134-meter diameter, and the wall thickness varying between 38 to 74 meter. So before the installation of this jacket, there were about 5 platforms that was installed, and then it was monitored because of the client requirement. But for this particular jacket, the contractor said it was not required because it is not a tender specifications, and then he demobilized the entire team. Although the equipment was there on board, but because technically I was curious, because the region that this jacket was installed is also known to have very wide lateral variation. So in real time, was getting the update that the piles were driven. The first leg was completed, the second and the third was very happy. But one morning, we got a call that the last pile was driven, but it refused 3 meters shorter than the target penetration. So I already said the philosophy of the principal clients, if the piles are driven to target penetrations because they have a high quality geotechnical data, piles are accepted. But in this case, it was suspected that the hammer was not performing properly, and thus the piles were not accepted. So how can we do the remediation on this? One is to make the assessment of the as installed capacity. So, but however, the piles were not instrumented. Therefore, the pile driving records, namely the blow counts and energy readings from the hammer console, were used for the pile capacity assessment with the assumption that the hammer was functional. So the wave equation program was used in simulating the hammer pile soil system, and pile capacity was back analyzed using a technique called the blow count depth matching. This is more of an hindcast analysis to match the blow counts using the energy from the hammer console. By altering your skin friction over the depth, it's a trial and error analysis, as well as the end bearing, and then you try to match the blow count. Okay, so again, I repeat that this hammer should be functional here. So with the assumption that hammer was functional, the capacity was estimated to be around 45.4 meganewton with the distribution between the skin of 22.4 and the end bearing of 22.8 meganewton. But now we need to verify whether the hammer was functioning or not for this capacity to be useful. But again, even this capacity was less than the intended capacity of 66.16 meganewton, and therefore the team has to be remobilized and perform a restrike test after 3.8 days of driving this pile. So when we actually do the restrike test, and the capacity evaluated by the CAPAP indicated a total capacity of 56.6 meganewton with a distribution of 47.18 against the skin and 9.3 towards the end bearing. The skin friction already is increased in 4 days. It's obvious because of setup, and because of the increase in the skin friction, the end bearing could not be mobilized. So in such case, the method of superposition will be adopted to compute the capacity by adding the end bearing from the end of drive and to the skin friction from the restrike test, and thus the total capacity computed was around 69.78 meganewton, which was more than the design capacity requirement of 66.16 meganewton, and the client did accept the files. So here is the force velocity time history. You see the velocity is above the force, and thus the end bearing was not mobilized during the restrike. And the CAPAP indicated total capacity of 56 meganewton and 47 towards the skin and end bearing of 9.3 meganewton. Adding the end bearing from the end of drive to this 47 yielded around 69.8, and it was more than the design requirement, and the client accepted. So in summary, most of the premature pile refusal can be attributed to unexpected lateral variation in the strata and their thickness. Cemented hard silt with crystalline gypsum strains or weak gypsum rock can cause refusal condition if its strength is underestimated during pile driving studies. Again, there could be a lateral variation, or there could be some kind of not evaluating the ground properties properly during the geotechnical investigations. We have to be very careful. And if the capacity requirements are not met, then plug drill out can be done to advance the pile to design penetration. Plug drill out done in stages with capacity assessment using CAPAP will avoid over drill out, which otherwise would cause a significant capacity reduction. And if not instrumented, the data is not available. From the instrumentation, the capacity can be back analyzed using the driving records and the wave equation, although it's very less accurate than the CAPAP, but this is only valid when the hammers are functional. So these are some of the references, and I take this opportunity to acknowledge my colleagues, Ramesh Ganjisetti, I think he's there in this presentation, Harsha Kadiyali, Srinivas Nagappa, Satish Arasi, Madhusudan, Manjunath Naglikar, and these are the guys who are there on the ground making those small decisions, but very important decisions to help progress of the project. I only backed those decisions and I presented the work that they have done. Thank you very much for this time. If there is any question, I'll be happy to take this. Thank you.
Thank you, Partha, for the wonderful presentations and excellent case studies in offshore pile foundation testing and drivability analysis. It was quite interesting. If anybody has questions, we take the questions immediately, or we take them at the end. I think we take them immediately, correct?
Yes, a short question. Very nice, Dr. Parthasarathy. It is always a pleasure to listen to you because of your past experience. I have just one small question on the Gulf case. So when you drilled out the soil plug, did you fill it up again? That is the question.
No, I think they did not do the grouting because the overburden was very shallow and 12 to 14 meters of soft clays were there. And without that also the capacity was achieved.
So but how much was drilled out? How much depth was drilled out?
Only to that 40 meters where the cemented layer was there, about 1 meter or 2 times the diameter, around 2 meters below the cemented lap. They drilled out and they could see the hard clay coming in. So therefore, there was not need to drill out anything beyond that. But the other cases, they will do the grouting where you cannot do the driving towards the target penetration. There are other remedial measures you drill and grout or run an insert pile as well. So that's very common remediation. In this case, they did not do any grouting.
Okay, that means it indicates that the plug length upon 50 meters was sufficient to mobilize that compressive capacity.
Yeah, that's right.
Yeah, thank you. Thank you.
You mentioned that there is suspected damage in the first case study. They suspected damage due to hard driving.
There was no suspected damage because they suspected because they did not monitor.
Okay, they did not monitor, so they suspected. So that was no PDA test was done on that particular
The first time it was not done. Now 1 year later, it was mobilized and did the restrike test. So that confirmed that the toe was intact.
Okay, but restrike, I don't know. You got to, I mean, because a lot of friction, you could still move the pile.
Piles could not be moved.
Because it's difficult at the toe especially.
So there were multiple trials did because we do not want to take out the cores beyond the tip. So the 3 trials were done. So every meter. So this was the 3rd trial I showed the presentation because of short time. So once every time they drill out and then before they drive, we did the monitoring of the data.
So any other questions?
Just 2 minutes, 1 minute only regarding this plugging again. That means, do you have experience of filling the plug again in some cases?
It's only grouting. Yeah, it's done. Most of the Middle East projects, they did the grout it back.
By which material?
I think cement only. They grouted with cement.
Cement only, not sand. Yeah.
No, it's cement. Usually those remedial measures is all grout with cement.
Okay. Thank you.
Thank you, Dr. Partha, for the wonderful presentation.
Thank you, sir.